Okay, good afternoon, everybody. My name is Nasem. I serve as the Associate Dean Research for the Faculty of Agricultural and Food Sciences. And I chair our seminar series this year. So if you haven't been to one of our seminars, this is to highlight our researchers and new work that's been happening across the faculty. And this year's theme is digital agriculture or precision ag or agri-tech, however you want to refer to it. And our speaker today is the fifth in that series with people from animal science in the past, plant science, food science, and entomology speaking on the topic. And today we have a soil scientist joining us. So I'll start with an introduction. We will have 40 to 45 minutes of the seminar presentation, and hopefully there'll be a bit of time at the end for you to ask questions. I'll try to moderate that. And for those friends or colleagues who couldn't make it here today, please let them know that we are recording the session. It'll be available on makemanitoba.ca as well as on our faculty's YouTube channel. Okay, if there is no particular question, I might as well get going. Great. So today's speaker is Dr. Nasem Badreldin. Nasem is an assistant professor in digital agronomy in the Department of Soil Science at our university. He received his PhD in geography from Ghent University in Belgium and his MSc in physical land resources from the Faculty of Bioscience Engineering at the University of Ghent. He previously worked as a postdoctoral fellow at the Center for Earth Observation Sciences, or CEOS, in the Department of Earth and Atmospheric Sciences at the University of Alberta, and at the Department of Soil Science at the University of Manitoba and the University of Guelph. He works as a modeling analyst, has worked as a modeling analyst in the Cumulative Impacts and Science branch at the Saskatchewan Ministry of Environment before joining us. So please join me in welcoming Nasem.
Thank you. Thank you, Nazem. Thanks for the introduction, and thank you everyone for being here. I know it's a pretty busy time, the growing season and all the field work. Before I start, I would like to acknowledge the work that my team is doing at the Digital Agroecosystems Lab. We are maybe 4 students with me at the moment, but we are working in a very diverse topics. The idea for the lab is to explore new frontiers, where there is a new technology or there is a new AI, I would say, or there is even a new question we would like to explore. So I have students that they are using spaceborne sensors to identify different landscapes across maybe 50 millions of hectares in the prairie, with a resolution to 10 meters, for example. And I have students that they are working with nitrogen concentration over a certain leaves, or even some disease detection, and even for crop yield prediction, using more than 60,000 farm data for 20 years. But sometimes also we revisit old questions and try to redefine them and see if we have the ability to see further, or are we able to analyze something with much more accuracy, or make it even easier for larger community, or even serve our bigger community at the Faculty of Agriculture, not just by ourselves finding a certain path, but finding different paths that hook us up more with different scientists and researchers. So thanks to them. And before I start, if you attend one of my seminars, I always bring something from history, because sometimes we are asking the same question or we are following the same path as maybe 25,000 years ago. I maybe pronounce his name wrong, but in Arabic we call it Socrates or Socrates. He never published a paper, but he's very famous. Maybe his H index goes to thousands, I suppose. Most of what he said had been attributed to him, so thanks to his students that they kept his words over. But this specific phrase, which said, "Man must rise above the earth to the top of the atmosphere and beyond, for only thus will he fully understand the world in which he lives," is actually a very magnificent word. Sometimes you need to step away to understand more. Sometimes you need to go back in time and zoom out to see much more connection in your landscape. in your soil, in your vegetation, in the life you are living in. This is an example that you see over here with the satellite images, mosaic satellite images, over 1 year of different seasons. What you see here is actually more than changing in seasonality. You see the earth is in dynamic motion. It's moving, it's changing. And there is a reason for the change. There are causalities. There are factors are influencing this. And imagine with me if we have a satellite image that you could see 1,000 years of change over the earth. You will get much more understanding of what been changed and to what, and start identifying some important features. For example, the moving or the change in the desertification in North Africa or near to the sub-equator, the change in the snow accumulation in the North and the South Hemisphere. You could even see more if you add additional layers of spectroscopy, or you add additional layers of ground truthing, or you do additional layers of field work or climate data and so on. You could see more. But the question we ask ourselves, can we hear more? Is this can produce also a sound? What I found lately by some scientists in the University of Tel Aviv, they had the ability to hear even ecosystem stress. There is a paper published in Nature listening to this. This is the plant is talking when it's under thirst or water stress. It's actually talking. This is an actual sound. That this in this paper, they said that's probably some animals also can hear it. So our environment is very dynamic, even to a way that produce sounds and produce information. The only disability there is us. We can hear or we see in more details. It's not a Morris sign, but anyway. Then you think about one of the most important things when you are measuring dynamics. The very fundamental question, in my point of view, or my lab, is taking resiliency or landscape resiliency very much seriously. We revisited the definition. And resiliency, basically, you put any system toward disturbance or stressors. For example, I'm here. When I started the presentation, my heartbeat just jumped in because of excitement, maybe a little bit of fear. But at the same time, am I going to function when I'm under the stress? How long it's going to take me to return my heartbeat to its normal? Those kind of things happen similarly to our ecosystem, our soil or the plant. You have a system or landscape system that under some sort of stress. And this ecosystem withstand and resist that kind of stressor, such as drought, maybe the loss of soil organic matter, maybe some soil loss because of wind, water erosion, maybe weed. Any stressor can happen to the plant or to the soil. And the thing is, you said, if this ecosystem can stay solid and keep functioning when we have that kind of stressor, that's the resistance. But another thing we also look at is the recovery rate. How much this ecosystem will return back to its own initial state, to its maximum. And the question we ask ourselves, what is maximum for that plant? Every ecosystem behaves differently. Sometimes when I get sick, I think about, am I going to return as healthy as I used to be before getting sick? Or there is a new normal life or new standard I will be facing after this stressor. This is the recovery rate. But also my team is focusing on the spatiotemporal dynamics. We would like to see, and we have seen something really amazing. When you put any ecosystem under stress, there is some fluctuation or there is some changes happen accordingly. But when you continue that kind of stress over time, day and day and day for 25 years, the responses of the ecosystem become much more fluctuating, much more nervous. And I will show you an example. Another one, for example, is the spatial pattern. Everything is happening within a sort of heterogeneity. So there is a corner of the farm or a corner of a native grassland is behaving a little bit differently. Is producing much more biomass, even though both of them, they are facing the same stressors. This also needs to be seen and heard as the sound we generated. Then we revisited some old definitions I had, and actually I'm using one of the figures I had in my PhD thesis. Apologies, I couldn't find better than this one anyway, but it's published, and we had some few discussion about it at Ghent University when myself and my supervisor, we were in the North Sinai, and we were looking to some desert area where naturally in your mind should be fully uncovered by vegetation. But some places were covered. They have the same heat stress, they have the same zero precipitation, maybe they have the same soil texture, but there is differences over there. And sometimes over the years, those ecosystems change. We call it a bistable ecosystem balance. There are two stages we defined, the good one and the bad one. And here I'm really giving an abstract, okay? And with those two stable conditions, the good one and the bad one, there is the unstable state where the soil start to increase the number of evaporation, for example, and the salt accumulation over the surface, and build up a soil crust that harm not just the pH or the EC or the electrical conductivity, the salinity itself, but also impact the physical properties of the soil. And we have seen examples. Our mission is to be here in those transition states where the environment or the soil is moving from one step to another, to catch that. But there is a problem with what we are trying to define over here, that it's all qualitative, it's all description, classes, and definitions. By chance, sometimes we can get something using satellite images, but we would like to be much more robust. When we speak about landscape dynamics, we are speaking, frankly, about differential equation. There is something moving over time, and we need to catch it, and we need to quantify it. And there are two major functions are judging the resiliency or the building a model for resiliency. The recovery function, which is also speaking to the recovery rate that we just covered up, and the carrying capacity, how much this ecosystem will return back to its initial state, but also the disturbance function, which is also dealing with the disturbance magnitude and the time of disturbance. Imagine with me you have a very high wind speed, let's say something that is 50 meters per second. With only 10 minutes, this could cause more damage than below 7 meters per second for even 1 month, right? So sometimes duration of the disturbance is important, but also the magnitude. You need to know how much this disturbance is building up or is causing changes to our system. We simulated every day for 25 years, and we look at two things. The above figure you see over here is the disturbance. These are random data we introduced to the computer. And at the same time, we are trying to see how much recovery this could be as a response to the disturbance. You have in the x-axis, these are days over 25 years, and also at the end you see some trajectory or projection to a future scenarios in case of further disturbance. What you see here, two things. First, the opposite response of the disturbance with the recovery, but also you see that the system is getting more fluctuation at the end. You see that there is at the end the computer start to learn how much this recovery will take. So there is a response over there, but we had one single challenge and we were trying to recover, which is these are simulations. These are not real data from the field. We need real data to see real scenarios. But before that, we went to another step. We picked 50 different scenarios of landscape, and we modeled those 50 different scenarios from landscape over 25 years. So the motion you see here within this figure is each dot here is representing one landscape, a farm or a native grassland or tamed or perennial location, or I would say forest or shrubland, and you will see that later. And each motion is representing some sort of what we call a tick, a move from one day to another or 1 year to another. But what is more important for us is to see the dynamics of where the disturbance and the recovery located. There are locations that have much more resilient recovery zone. They have more disturbance, but they still recover. There are the optimum or the optimal stability zone where they have no disturbance, and even the opposite, more rainfall, more organic matter, but still there is a sort of recovery or latent degradation zone. Whatever you are doing over there, the system will decline anyway. This is very useful for decision makers, because now the decision makers can select a specific location and build their own long-term strategy for recovery or applying nature-based solutions. What we notice from this dynamics, there is a special pattern. You see that there are vertical and horizontal movement, but at the end, they move in this kind of zone from resilient recovery to the latent degradation. There is another way, which is also to the enhancement to the ecosystem itself, moving slowly from place to place. But the most important thing for us is to catch the transition within the ecosystem before it landed over that stable system we discussed before in the previous slide. But also there is this kind of dangerous or sudden death, as I call it, that system change immediately from location to location or from status to another. For example, you have a landslide that changed all the vegetation cover. You have a huge wind or water erosion that creates some sheet erosion and so on. And from that also gives us a lot of good information. Again, you are looking from the space, looking over the prairie, and you don't see those details, but it shows up in the modeling. Now we come to the first problem we faced. Where to find the data, and how can we build up our analysis more robustly on real scenarios? If you attended one of my previous presentations, you will definitely heard me talking about the FAIR model. How can we use the FAIR model to engineer and build a clean data hub? What we call it is the FAIR. It's not our published work. It's another people's work, actually. We are using it, called the findability, accessibility, interoperability, and reusability of the data. They need to fit under this category. And after that, we've been surprised with the amount of data. We are dealing with maybe 5 terabytes of data in a multi-temporal dimension. So we call a 4R data stewardship, and I was joking with one of my colleagues about the nitrogen stewardship. So we stole this kind of word from him, the right source, the right format, the right purpose, and the right audience. And we starting building an application that adapts the philosophy or the strategy we are trying to develop. You see here, in this little video, I'm showing here a new application. We call it TerraQuest. This is open for everyone. If you scan this code, you will access to this application. It's a web map using JavaScript, available for everyone. What you can do with this, you can zoom in any place in North America, and you can get every 16 days of NDVI, for example, vegetation index. You can get a fraction of photosynthetically active radiation. You can get leaf area index. You can get daily precipitation. You can get daily maximum temperature and minimum temperature. You can get shortwave radiation. You can get vapor pressure. Everything within one click. You just have to create a polygon in your case study, like you see here in this little video. You will be able to get about 25 years of data, and you can convert it to a CSV file, and you can take it from there and build your own script using Python or R or whatever kind of programming languages. You don't need to download any satellite images. You don't need to download any climate data. You just have to delineate. You will ask me about the sources, where did you get this data from, and all of that. Everything within the application, you just click and go. It's super easy. We call it 0.2 because still in the trial. Hopefully in the new year, we will have version 1, which is available for the external users. But anyway, it's available for everyone. I will let you enjoy the exploring this application. Anyway, so what we did is actually going and using our own tool to get satellite images of every 16 days. But this is not enough for us to tell the full story there. We need to know every day kind of NDVI, for example. So what you see here, there is one location NDVI responses over from 2000 until 2024, from the time of the 1st of April until the end of October. You have here little purple dots. I hope you can see them. These are the actual measurement from the satellite. So these are the NDVIs coming from the satellite. What we did is we use different models, 6 different models. Don't ask me why did we choose those, but they seems in the publication pretty good in the predictions to fit and try to build up a prediction to generate every day NDVI over any location we want, and also for the other parameters as well. And from that, we got really low root mean square error for 2 models. One of them is the locally estimated scatter plot smoothing, but also there is the sigmoid, which is also providing some sort of really low error over there. Again, we use the root mean square error to highlight the outliers and make sure that we are not picking any, because our game here is to look at the maximum peaks and the minimum. You could see here basically the 2021 low response, which is a very dry year across Manitoba, for example. Again, what we did with this kind of models, we try to generate what we call it the hypertemporal resolution. So now we are able to have everyday NDVI and all those kind of variables that will be used for resiliency or for resilience modeling over any case study we want with a minimum required computing power. And that's also another thing. We are also not very rich lab, so we have to be creative with our tools here. Anyway, what you can see here, some artificial boundaries here, and that's because of the lack of prior data for the models. So we can clip this easily, but also at the back of the season, which is the end of October. But at the end, you could see the daily changes over the NDVI. We use for accuracy assessment the mean absolute error. Again, we are using an opposite strategy than the root mean square error. We don't want to really highlight, in this case, the outliers, since we are confident that what we get is enough. So we got something about 0.1 plus or minus, less of the time error with the vegetation index, which is pretty powerful when you think about it in a longer time scale. But it's also part of really useful material for our predictions. Now we have the data, we have the question, we need the body, we need the case study, we need to work with something. One of the things we work with is the grasslands. And I would love to thank my student who done a really great job on identifying really new strategies to expose and understand more about native grasslands in the prairie and in Canada. Well, you all know how important grassland ecosystems for absorbing or carbon sequestration, but also how important they are for biodiversity, for the soil and water conservation. But also one of the things that strike me as a soil scientist when I talk to some old generation ranchers in the south of the divide in Saskatchewan a couple of years ago about how important they learn from the indigenous people that they have to ranch over natural grasslands because it reflects positively on the quality of the beef itself at the end. They kept it in their mind, and I was talking about your landscape, your native grasslands are actually disappearing somehow. And he's willing to invest in the biodiversity and return back this dying ecosystem for just this kind of wisdom they inherited in the land they have. Anyway, we took another step and we're starting to see, okay, what is the problem or what kind of disturbance the ecosystem in Manitoba is facing. We looked at about 8 million hectares at the moment, just a test to see if we can catch something. We compared 2013 with 2019 for several reasons. Technically, because we want to compare two similar technologies and approach. We had a very long, unpleasant discussion with the AFC, but at the end, we reached out to a step where 2013 and 19 are really the longest, most trusted 2 years of comparison. We discovered that there is 95 case of dynamics with this range. There is a wetland that changed to shrubland. There is a grassland that changed to a wetland. There is a wetland that changed to cropland. And there is a cropland that changed to something else. There is a dynamics there. And if you look at each year in those 7 years, you can see something. You see a decline or a change of grasslands to cropland, not directly, but through different steps associated with the disturbance or the droughts that happen within that year. So there are some causality, even though we couldn't pinpoint or identify which one exactly. We identify 5 major disturbances as one of the things that harm the resiliency. Brush encouragement, the shrublands movement toward the grasslands or native landscapes, land degradation, including salinity, erosion, etc., depletion of soil organic carbon, cropland conversion, that's another human or man-made activity, drought and wildfire also being part of those. One of the major disturbance that we found in our native grassland is actually the shrub encouragement. When we looked at the data, and I want you to focus on these red spots, which is indicating that there is a landscape that's been changed to shrubland, whatever the landscape is. And within those red rows, those are the most scary ones for us. The grassland that changed to shrubland, 53,000 hectares within 7 years. Pasture to shrubland, about 10,000 hectares. Wetlands to shrublands, 65,000 of hectares within 7 years. The problem is even bigger than this. We noticed that there is an annual change from grassland to shrubland with about more than 7,000 hectares per year. There is, forget about the pasture to shrubland because it's slow because there is someone is trying to stewardship this landscape. But you could look for grassland to pasture and then you see more than 16,000 hectares per year are changing to that. Grassland to cropland, more than 20,000 hectares per year are lost from our precious ecosystem that has the power to sink carbon to become a cropland. The question is it a successful cropland business? That's another question to ask later. But anyway, these are pictures from the field. You could see the silver sagebrush encouraging. Most of the time you see that they are near to some roads. So it comes with some movement or seeds that been transported, not intentionally. Anyway, we ask ourselves another question. Okay, now we may be able to measure resiliency, but are we, with the existing data, is this existing data is enough? We identify a new, what we call it, a 2-step landscape intelligence process. We call it intelligence because we want to sound intelligence. But anyway, the idea from this is if you would like to understand the resiliency of something, first you need to know what are you looking at. Are you looking at cropland or wetland? Or what kind of wetland? What kind of native grassland? What kind of crop? Is it pulse? Is it soybean? Is it canola? It makes a huge difference to know what is the type of landscape. So we started with landscape identification. That's our first step to start building up a resiliency modeling approach. Landscape quantification. Now I know that I have this amount of native grasses, but do I know how much biomass this native grasses is producing every year? Do I have any idea about what kind of yield this farm is producing every year or every month, or how much this is growing over time? These are questions my students answered actually. So we reverse engineering the whole thing. We're starting with the question, opposite that some labs that start with the tools. So we started with the question and then we look after and say, okay, what can we do to answer this? Okay, we need sort of pre-processing to the data. We need data fusion. We need to import or to use much more supervised machine learning algorithm. We need to enhance the existing data, for example. Do we have enough in situ measurements? How can we get enough ground truth? That's very important for us, how we can go further, how we can collaborate with others. And we have even a student at Ghent University who is accessing to a global soil spectral library and building some interesting universal prediction equation for soil organic carbon. We use also the UAV, for example, the drones, to even empower ourselves in the field and get much more ground truthing. But at the same time, we're also investing in the CubeSats and the low orbit satellites. And actually we invested more than $20,000 just getting enough CubeSats data to understand, going back to Socrates, how far shall we go in order to see all the dynamics we want to see. We are like everybody now, it's a fashion to use AI. So we used AI. We used the supervised one of the AI. And basically, before the AI, we used to have the algorithm and data and generate the output. But basically, what we do with the AI is we have the data and the output. We have the spectral reflectance, but also we have the chemical analysis. And we put this toward what we call it a black box modeling, trying to find a relationship or algorithm that explain two things. Either we do a regression to predict something quantitative, or we do classification to distinguish between two things. And it fits toward the two-step intelligent process system we are developing. For that, we generate several data. We had more than 68 layers for Manitoba, Saskatchewan, and Alberta, as you can see here. We're using different satellites, optical and SAR, Sentinel-2 and Sentinel-1. We use digital elevation models. We included also different vegetation indices. And in addition to that, we have also a temporal frequency. As I described in the resiliency, the recovery rate is need to be catched within. So this is an example of 4 different times or seasons within the period between May and October. Of course, you would see some exposed soil, and at the end you will see some exposed soil as well. We would love to catch the changes toward the biomass or the above ground biomass we have. Oops, it jumped. Excuse me. Okay. For that approach, we've been successful to get the whole prairie native grassland classification. And with some reasonable accuracy and with really a lot of amount of ground truthing, that more than 10,000 ground truthing points, thanks to the, what they call the CFGA, the Canadian Forage and Grassland Association. They invested in our partnership and they put people in the 3 provinces collecting actually ground truthing to identify what is native, what is tame, and what is mixed. The definition of those, we will see them in a paper if you are interested to know what are the names of the species under each one of those. But at least we've got some reasonable accuracy. That wasn't enough for us. We wanted more than 70% of accuracy. And because of that, my students start to develop a new technique. We call it the hierarchical AI strategy, where it goes into loop of analysis. Each step of those exclude what you don't need. Basically, what you do in the AI is target what you need. In this case, we actually target what we didn't need, what we don't really want. At each time we catch something we don't want, we kick it out of the system or we kick it out of the analysis. For example, we started with a really simple question: what is vegetated and what is not? Is the AI able to capture vegetation from non-vegetation? It's easy. Did it with a 90+ accuracy, right? Then after that, we have pixels of vegetated land cover. From those vegetated land cover pixels, among this 40,000 or 40 million hectares, you will be able now to do which one is grassland and which one is non-grassland, regardless. Then we've been very good at that, and we catch that. And from there, we will be able now to catch which is native, which is tame, and which is mixed, which will bring us really a pretty good accuracy with some additional data enhancement. This kind of work faces a lot of challenge, comes from the field to the satellite images. I remember one of the famous scientists used to call us a couch scientists. When he see us, he's a very famous soil scientist, Eric van Ranst, used to be the editor-in-chief of Geoderma, and he saw a bunch of grad students sitting and he said, "You guys are sofa scientists." But actually, sometimes we go outside in the field and we do some work outside and see how challenging it could be. These are the challenging you could face in the field when you are collecting ground truthing for the AI to predict robustly. Think with me, those are more than 10,000 points. You have to go over each one by one. Anyway, so you could see that students sometimes just, enjoying the road, clicking or disappearing in the woods. I don't know what they were doing here, actually picking samples here, or just near to the fences. But at the end, we had a pretty simple algorithm to kick out all those kind of weird data. With the satellite images, with the optical remote sensing, with a big area like this one, you may face a lot of challenges, cloud, atmospheric changes, and so on, data availability. We work with some data fusion, image fusion, mixing different types of images, and making sure that we are enhancing the quality of the images by providing much more spectral resolution or even spatial resolution. We use two of those different kind of systems, the HSV, which is the hue, saturation, and value, and also we have the Brovie transformation, which is also added within this analysis. Enhanced in some cases, but in some bands, it doesn't provide really that kind of much accuracy we are looking for. But at least we tried the approach. At the end, believe me, the image should look better than this. It's much more details, and probably this is the problem. It is every 10-meter pixel size, but you could see here with a clear indication of how the invasive or mixed grassland is or are encouraging toward in a native place, in a native grassland. Imagine with me if you have this over the years and you could see the dynamics over that front. Sometimes it's because of the prevailing wind direction or some agriculture activity that push further those kind of mixed grassland. There are a lot of insights we can generate from those kind of multi-temporal maps. Another quick one, which is now we've done with the two things, the identification, now is the quantification. We needed to know how much above ground biomass from this grassland. We have a very good collaboration with the AFC. They provided us with more than 90 ground truthing of biomass over 2 years or 3 years. And those locations are distributed over Manitoba. The question we had is these data or this kind of data inputs are not enough for any AI. 95 is not enough, but also at the same time, you see the data is not normally distributed. We need also from the other edge of the biomass. We need the low biomass as much as the maximum biomass to train our AI. For that, we had also within the investment I was talking about, the CubeSats, what's something we call it the biomass proxy. The PlanetScope, actually, or Planet Lab Geomatica, it's a satellite company. They launch satellites. They give us very precious data over every day for the past 5 years. And for that data, they have a proxy of the biomass, not an actual measurement. What we did is, with the 95 data ground truthing, we try to match the biomass proxy with the ground truthing in order to find the relationship between those two in those different times and build up a very simple model that will allow us to generate much more quantitative data. For example, you see with this figure in this X side, you see the time from the field sampling. So 0 is the exact day of field sampling, and pluses are the days after the field sampling, and the minuses are prior to the field sampling. The satellite path through that time, every day we have a data, but which one of the satellite data is much more aligned with the field sampling? What we found so far, that -7 days or -5 days in the field sampling from the satellite images align perfectly, somehow perfectly, it's not very perfect numbers here, but at least somehow perfectly with the ground truthing, which means that we, within this exponential equation, we can actually build up a regression model that can interpret and see much more about our actual biomass, gram per square meter. And what you see here as synthesized data generated from the real ground truthing plus the field or the biomass proxy we had from that satellite company. Of course, it is very sensitive, meaning that if you change any unit, things can change very dramatically. You could see this shifts is a response to the sensitivity of the model itself. But what can you see here is further than that, the explanation to some drought event where the biomass been shown perfectly in 21. That's the kind of benchmark or the area where we look and see if our model is responding perfectly. You'd see here again, the green line here is the average. Each line here is representing one of the field sampling location. And here is the time scale from the 1st of May until the end of 23. Again, we are also between April to the end of October. And you could see clearly how all the points are responding perfectly to the changes over the biomass we have over here, and also within the precipitation that this area is showing. We moved forward with that because what we have is just a point prediction. What we want to generate actually, it's a map of the biomass over different times. And for that, we use 3 different satellites. We have the PlanetScope with 3 meters spatial resolution, Sentinel-2, which is the European one with 10 meters spatial resolution. We have Landsat, the American one, with 30 meters spatial resolution. Sometimes the high resolution doesn't provide much more accuracy. We need to test that. We use the Pearson correlation coefficient just to see how these variables or these spectral variables, bands and vegetation indices, in addition to the biomass itself, are interacting with each other. We would love to see if those variables could be an adding value to the AI or just will create some hallucination to the models. What we found is really an amazing result, especially with one of the machine learning algorithm. We call it support vector regression. We use it 2 different scenarios here. The blue one is with all the features in, and the red one, all the features in except the digital elevation model and the climate, because they're a little bit challenging when you do the data acquisition and enhancing, and also you have a multi-temporal. What we found is the Sentinel-2, for example, provide quite good predictions, but what our eyes actually are at is not the R-square, is the root mean square error, where we have about 22.45 grams per square meter error. That's a good number according to some experts. Anyway, at the end, we were able to map the biomass of our case studies at different times using those 3 different satellites. I'm about to finish within a couple of minutes, if that's okay. We have few messages for you. The first one, we can be able to do all of those, enhancing the observation capacity, overcoming operation barriers, and even decision-oriented modeling. We become much more super capable of that. One of the challenges, actually, the scientific understanding, the very fundamental of what we are doing and why we are doing it. Is the question we are tracking is a reasonable question, or if it is useful for the further clients or further stakeholders? Is it just going to be useful for scientific community, or is going to be used for actions in real field? That's another thing. How can we be more accurate and confident about our accuracy? Because most of the time we are dealing with uncertainty, because these features that we are putting in our models are very sensitive. Any change in the drought, with some change in the soil organic carbon, whole thing can change. How sensitive these systems are, and how we can be very clever at this. Other thing, what we call it the flying labs limitation has real limitation there. We have to identify it. Not every tool is capable of doing everything. We identify our tasks to objects, single object properties. If I need to know the chemical properties of something, how capable I could be using these tools. LOS is the low orbit satellites. GeoSats are more further away satellites used for climate data most of the time, like the NOAA. Multi-object properties. Am I going to be able to catch multiple trees and do the biomass prediction for those, or it will be limited? And what are the limitations? Object dynamics, and so on. I don't want to go over each one of those, but the Digital Agroecosystems Labs actually looking at those yellow things, the more challenging ones, to see how can we improve this kind of tools to get more about our ecosystem. Last but not least, our last piece with the conclusion, we are actually moving even forward. We are looking at every crop, at every variety for each year, at each farm in Manitoba, between 2000, I believe, and 5 until 2025. For that, we will be much more able to do predictions using the concepts I introduced today to you, in addition to the tools we are building. This is not the end, this is the start, and hopefully for a good one. So at the end, thank you very much, and looking forward to your questions. Thanks.
Fantastic. Thank you very much, Nasem.
Thanks.
Excellent presentation, very enjoyable. I learned lots. So let's open the floor to questions.
Yes.
Anybody wants to break the ice here? I don't see it yet. Doug is pretending to ask a question. Oh, I see Michelle first. Go ahead, Michelle.
The ground truthing of the biomass, was that like students actually going out and biomassing at certain points? Or
No, the AFC. The AFC. And they have some locations where there is no ranching or grazing because this is very sensitive. So we've been very sure that those are not exposed to cattle or any livestock. So because now it becomes very sensitive when the satellites are passing through that time in that location. So it's actually done by an actual ecologist from the AFC.
Great. I saw a hand up go there. Yeah, Rita, go ahead.
Thank you so much for the presentation. I'm sorry if I missed during your presentation, but the question is, why is the transition of grassland to brushland is bad? Kind of? I mean, I can understand
Yes.
cropland or pasture, but is it reducing carbon sequestration or?
For the shrublands, you mean the shrubland, the brush encouragement? That's a good question. It's not about actually the carbon sequestration. It could be about the soil moisture that the root system is competing with. In addition to that, you have to understand that shrublands sometimes they are very trigger to wildfire in some locations. In addition, they have a very low economical input because they are prohibiting the ranching process itself, like the cows to go and eat and so on. So from the environmental point of view, they could be much more susceptible to drought and cause a lot of wildfire, which happens a lot, by the way, especially with the grassland. And in addition to that, economically, it could be very damaging to a ranching business. They don't want to see it. Even though sometimes it's really good for some species at risk. You know, there are some, what we call them SAR, species at risk. There are some species in the prairie are really at danger because of our agriculture activity or even, what they say, the southeast of Saskatchewan, you will see a lot of oil excavation and a lot of that. And those kind of human footprint are increasing, pushing forward, and even disturbing a lot of beautiful wildlife that flourish our ecosystem.
I was supposed to hand this over to people that ask questions. So who is next? I'll come by.
Thanks, Nasem. Yeah, just a question about, so this TerraQuest?
Oh, yes.
Yeah, tool that you built. So is that built in Google Earth Engine?
That's right.
Okay.
Google Earth Engine using JavaScript code, but
Yeah.
it's an application.
Okay.
You don't have to go to the editor.
Yeah.
You don't have to deal with any coding. What you do is plug and play. Or
Yeah. So my cheeky question is, why didn't Google Earth Engine just build it that way to begin with for researchers? Because that seems like an excellent tool that we all want, and then we don't need to learn Java.
Yes.
And then my real question is, so you say this is an early version. What are some adaptations you want to make in the future, or what are you still working on tweaking with it?
Very good question. Thank you very much. Google Earth Engine, they are providing platform. They are not keen really very much. They are opening it for the scholars and the scientists to just explore and see what can we do further. Maybe they will sneak after and see what they can use for commercialization later. But I have seen some examples, not in that detail, but just using NDVI for some locations, using some satellites. And then it came to our mind is like, okay, what is the data hub there that contains or in Google Earth Engine? What we found, they have a gold mine of data just sitting there, nobody's using. So we ask ourselves, can we develop something as simple as drawing a polygon and just click and then put the time frame, and then you don't have to download any image and you get the data? What is in the application also some downscaling technique using AI. For example, the climate. The climate is actually an interpolation from the NOAA or from other resources, which as I left over there. But what we did is actually downscaling it to 30 meters instead of becoming 1 kilometer. You know, climate data are really difficult to get and put together. And sometimes you don't know how far you are from the point or station. So I don't want you guys or us to be bothered by something as simple as, you know, looking with which station is working and how long it is working, right? Because at the end, what you see here is interpolation across North America. And by the way, this data, especially the climate one, goes back to 1970 something of every day until today, I think, until today, up to now. So anyway, that's one. The second one, what is next? Well, My team is making progress in other fronts, right? They are doing some additional results or additional data. That's also in the map to be put over here. I have students that they are going to start in soil organic carbon mapping. We have a couple of papers as a proof of concept, how to map or predict surface soil organic carbon using PlanetScope and Sentinel and those affordable, again, the FAIR model there, right? So at the end, if we have a big map of soil organic carbon within the top 5 centimeter, I would love to have it in such an application where you guys just draw a polygon over there, click, and get the data immediately. So it's becoming a living, let's say, application that each time we are putting a different layer. Yeah.
Fantastic.
You're welcome.
Okay. Any other questions? Yeah, Jite.
Thank you, Nasem. Very easy question for you. So in your satellite, did you have problem with the clouds? And
Yes.
How did you deal with that?
Oh my God, yes, this is a pretty difficult problem. Though we had a problem with Sentinel and Landsat, right? For the people that they don't know about the optical remote sensing, they are always challenged by the cloud coverage. What we did is we moved a few days in a range for some places. Let's say if I have this area and I have the corner of this area for that date is cloudy, we just clip out that cloudy piece and go for another tile, which is kilometer by kilometer, and puzzle it. But the only challenge we had at this time is how far can we go back in time? Because you need to find another day of the revisit for that satellite where you have a pretty good clearance over there to see the landscape, right? It was really, really tough work. It took us about a year to get this kind of big mosaiced image of all Manitoba, for example, or even for the prairie. I would love to share with you that kind of data for 10-meter multispectral, but it has to be built patiently. This is something that the AI, we are not very confident to use the AI for cloud removal, even though I have seen some papers in IEEE journals where they are very technically engineering some sort of approach to remove those clouds. But it's not just about the clouds. It's also about some other disturbance. It could be a wildfire that happened within that kind of spot that will become much more different than the other or the rest of the image. It could be also the shadow. Remember when I was showing the ground truthing? There are some shadows from the trees. I have a ground truthing under that shadow. So again, it's a chase game over there.
So like one of your mosaics is actually made up of different dates. Right?
It has to be, but not far. So within months, those are the pixels. But when you go at the model, as I described in the middle, with the one with when we did the fitting for all the days, no, that's pretty accurate because we use for this MODIS. And you know MODIS satellite has this kind of daily or every 16 days kind of revisit. They have the Aqua and Terra, I think. So they have different sensors are passing in 2 different times, and each one catch a scene within 16 days. So you always have a clearance over there over the time. Yeah, oh, good. But also, let me please continue this. Also, we use SAR, synthetic aperture radar. This is pretty good with the cloud coverage because it doesn't care about that. Yes, thanks.
Thank you, Nasem. Very interesting presentation. I'm wondering if you have kind of cross-checked the weather data that you get from this app with the weather station that Manitoba Agriculture maintains. We have over 100 of them across Manitoba, and then there is another source at Environment Canada.
It's pretty accurate,
okay.
And it's already been used. Again, you have to realize that this is interpolated. It's impossible to have a station every 1 kilometer. So it is validated and published and been posted. I have the reference. I don't remember it from the top of my head, but you could look at. There is a link we called info. When you click in it, you will see from where the data coming, which is pretty accurate resources, including, I think the NOAA and NASA and other parties, they are participating in generating this kind of North American daily climate data. But again, you have to really, take some risk over there with some uncertainty. But again, that's the best, I would say, the best bet of having every 1 kilometer climate data. Again, those are also being downscaled. So you have every 30 meters actually climate data.
Good. Yeah, we have like some challenges for the crop yield prediction model. We're kind of trying to build assigning field to stations. Some of the stations
I know,
are far from
yes.
the field, and
It's challenging, yes, and that's the purpose of having such a tool. Making it easy and give you more time to think about more deeper question instead of wasting all of your time looking which is the best nearest station. I think Martin and Manasa.
Oh,
I think Martin raised his hand first. Sorry, Martin.
Yeah, thank you, Nasem, for your presentation. I'm just wondering, because in most cases with the weather data, it's accurate maybe for temperature. Do you find it to be good for precipitation?
I found it pretty reasonable when we compare the biomass proxy. The biomass changes over every day in the 5 years, that there is a high correlation between, I would say, the drop of those precipitation or the decrease of the precipitation and the decrease of the biomass. I'm not so sure if the numbers are very accurate, to be honest. It's not us who collected this data, but at the end, I'm looking at the responses of that drought or the lack of precipitation and see if the biomass is going to respond, then there is something going on there, it makes sense. If not, then it becomes a question. But again, I'm not mentioning here this is the high end. This is again V.2. So we are aiming to reach to V1.01. And I need your help to go there, find the problems and tell us. Until now, we couldn't capture any problem. Maybe we are a little bit biased. But I advise you, please go there, everyone, and look and try your case study and see. And if you find something, let us know. We would love to be super accurate. Thank you.
Was there a question?
Martin, he has a difficult question for me.
Yeah,
I was praying he's not going to ask.
Okay, thank you, Nasem. That was really interesting.
Thanks.
So, thinking about your PhD and the change in state, I guess, I was intrigued by the model that you had, the 4 boxes,
Yes.
and you looked at both the sort of the negative effects, and then you also looked at interventions that had a positive effect. So you had, I don't know how much that has to do with all this, satellite weather data, but I'm just wondering, have you developed some, I think way further back, have you developed some scenarios for the prairies that would describe a positive intervention? That really intrigued me. And I'm just wondering if you have thought about examples of where you either sort of, are moving from a positive to a negative state or the other way around.
Yes.
It's the green arrows maybe.
Yes. Yeah. Yes, you're right. That's part of what we would love to see real examples. At the moment, what we have done so far is picking 50 randomly locations and try to see the dynamics. From that dynamics, we notice this kind of multi-temporal movement, or not a spatiotemporal, it's just temporal movement. This, what you see, is a temporal change of their status. So within the 25 years, they are changing. Each point of those is a farm, for example. And they are changing every year towards something. Or they are backing, or they are going to something and returning back. Those are, at the moment, just a simulation based on NDVI as some data we captured. But at the end, the end of this, we need to look at real scenarios where we know for sure that there is something happen specifically. Because one of the difficulty we have at the moment is causality. I will give you an example. You're losing a certain landscape toward another type of resiliency, and you are assuming that the drought is leading to that. It seems to be obvious to everyone with the numbers we get, is the drought the reason? But actually, it could be the soil carbon is leading toward less holding capacity to the water, for example, which has much more impact, but not seen one. You see my point here? So there are some hidden factors under those. That's number one. Number two, every year is a different scenario. So now we have this. Let's say that we understand that the soil organic carbon loss is causing the low soil moisture holding capacity, for example. But maybe next year there is something else will be introduced. The models up to now can't catch those two. So we are trying to find a way to do that. I don't know how, but we will do it.
Okay, we have one last question from Michelle.
I'm wondering if you could use long-term trial data to kind of answer some of these scenario questions on the long-term trials that go on across the prairies.
I was thinking about that actually, and the paper you published about the 20 years or it's 25 years, is it the one that you're mentioning, right? The one with the long-term measurements?
I think we were like Scott's sketch of like all kinds of different long-term trials where data has been collected every single year in archives.
That's a beautiful thing, yes. That's just last week. I was in the University of Georgia attending a course in DSAT. It's a decision-making tool for agro-technology. I think it's for creating a scenarios and based on some agriculture management and to see the crop yield and see all of that. Actually, I was attending it on behalf of my student who couldn't get the US visa. So anyway, the point is there, one of the problems within that model that creates scenarios is they didn't have enough experimentals or trials to build a really robust model to understand the changes. If we have a data like this, that would be super cool, because once we can catch the pattern, then we can put it immediately toward the remote sensing, and it will be easy to build up a historical predictions, even forecast for the future with different scenarios. Like if you have drought this amount, another thing, I was looking to something, they call it crop rotation kernel. Crop rotation kernel is, you have a sequence of crop rotation, right? You cultivate this, next year you do that, next year you do that. But within 25 years, that kernel change. The question is why? That's also another thing we are looking at. Hopefully you can find an answer.
Okay, we are out of time, but please join me in thanking Nasem for the presentation and the questions.
Thank you.
Thank you, everybody. That closes our seminar series this year. So keep your eyes and ears open for next fall series. So we'll announce that.
Thank you, everyone.
Have a great summer. Thanks.